Hello everyone, this is Mohsen Saraj from Ozen Engineering. I'm a senior application engineer for Ansys Safety. In this video, I want to talk about how to model open channel flow in Ansys Fluent by volume of fluid method. Okay, this is the model I developed in Discovery. As you can see that we have trapezoid cross section for the channel. We have two channels, okay, that joining together to a larger channel, and I extended it a little bit longer, the bigger channel, to be sure that we see the good merging of the flows coming from each of these two channels. I already defined the inlets. As you see, these are two inlets here. Also, I have one outlet there. Bottom that we use it for defining the bottom level, and walls here, as you can see, for the walls of the channel. And also I call the top surface as open. We will see that how we can use these boundary conditions here. Nothing special more here from the geometry, and let's go to Fluent and mesh it. Actually, I already did that. Okay, I transfer it as a watertight geometry workflow to Ansys meshing, and then have the mesh transferred to Ansys Fluent. Here it is Ansys Fluent. As you see that I already activated the gravity in a y direction, and it is transient simulation. For the model, I activated the volume of fluid method with the option for open channel flow activated. The default number of phases, it is 2 phases, and also I checked in the implicit body forces. We have 2 phases here, as you can see, one phase for air, second phase for volume, for the liquid water that I already defined it here. Okay, if I use the material box in Fluent, I always can define the new material here. For example, okay, like if the way that I added liquid water, if I copy that, I can see the water liquid here. The most important thing is the density and viscosity here. So back to the phases in volume of fluid method, we have primary phases here for air, that I choose it air here, and the secondary phase that I choose liquid volume, liquid water. Usually we go with air for whenever we have the air and water in volume of fluid method, because air it is lighter and has less density. One more option that here we have to also work on, that it is the interaction between the phases. The default is none, okay, but I consider constant surface tension between the air and water at the free surface with this value, and I activated the continuum surface first for the force modeling for surface tension. So everything is set up here, nothing more, and the energy is off because here I don't apply the boundary condition for the temperature or heat transfer boundary condition. Here we don't have any. We already also defined the materials. For boundary conditions, for inlet, these are the inlets that you can see. I choose pressure inlet, and we have 2 tabs here, momentum and multiphase flow. Okay, for the momentum, nothing special here, we just keep it as is. For multiphase, we activate the open channel. We have to specify where the free surface and where is what is the water level at the inlets, and I choose only 0.03 meter, so it is only 30 centimeters, so it is very shallow, and the velocity it is just 1 meter per second. We need to also specify where the bottom level is. This is for inlet. For outlet, over there I use pressure outlet. Momentum, everything is as is. Multiphase flow, again I have to define what is the level of the water and where is the bottom level at the outlet. Open is the top surface that I just leave it as is. Consider gauge pressure, so it is open to air. And this is for the interior and walls. So these are the boundary conditions. For the solution methods, I use piezo, and piezo for the scheme for the coupling of the pressure and velocity, and for pressure discretization, Presto is recommended for volume of fluid, and second order of wind for the discretization of momentum and other things. We leave the residuals as is. We can go for initialization. Also, we can set some reports here, okay, based on what we want to define to monitor the velocity, pressure, or whatever at inside the domain, the whole domain, or at a specific location like an inlet or outlet. Here I define the velocity, volume average volume average velocity for the whole interior, and pressure at the outlet, to see that if there is any unexpected results that here we can see. For initialization, you can just go by what is given or from all zones or whatever. I already initialize that from inlet, and as you can see that the water inside the whole domain, okay, at the very beginning, at the initial, is considered 0. But we don't want, because we don't want to go to filling the channels, but we want to see that if the channel water level it is at 30 centimeters, we have 1 meter per second at the inlets and outgoing flow at the outlet. What is the flow conditions after merging into this big part here, okay, and what is the surface waves velocity, and also what is the water level here. So we need to say this to Fluent, that at the very beginning, where is the water level. We use patch, okay, and we can define where is the water at the initial time. I choose a volume fraction of 1. It means that the where water we have, and I already defined a region to patch this together and patch it. But before that, I need to define the region that I already done. I name it region underscore initial, and based on the dimensions at the domain that I have, based on the geometry, I choose these values for the x dimension, y dimension, and z dimensions, and I consider 30 centimeters for the water level at the whole domain at the very beginning. Patch it, okay, and close it. I can also if I want to define some event for autosave here, or for the animations, I already set it up. Before that, I define ISO surface, that here I assign the ISO surface to where the volume of fluid for the water, okay, is zero point 0.5. It means that 50% water, 50% air. It is a kind of showing that where the free surface is between the air and water. And then use this, okay, use this, I call this ISO surface. For the free surface, I call it free surface myself, and assign the velocity magnitude to that. So when I created a scene or an animation or whatever based on this contour, I can see that what is the velocity at the free surface. So based on that, I created different animations based on the contours that I have. I will show you later. So these are the things that I can do before running the solution or the calculation. It is based on what I want to see here. I can define different contours or more isosurface or whatever I want. I did some of these. For the setup for the solution, I used the very low time step, almost 5 milliseconds. It depends to how many time steps you want, how long you want to run the simulation, and I just keep the default value for the max iteration for every time step. If I hit and run this calculation, you can see that the results here after finishing this number of the calculation. So I stop here, and after finishing the calculation, I back to you. Okay, calculation done. As you can see that almost 9,000, 10,000 time steps already ran this simulation. Here, these are the animations that I created. For example, it is only for the free surface. Let's go to the result, and here for the animation playback. This is for this one, for free surface. This is inside the channel. For example, if I play that, you can see that the flow from two channels are merging here, and this is the initial time that at the very beginning have the flow develop inside the channel, as it is long enough to see that have the waves over the surface developing and merging. And here you can see the range of the velocity for that at the free surface. This is also from top view. You see that they have the velocity developed, have the flow developed inside. As you see that because of it is very shallow, we see that somewhere here, for example, we don't have really water, and over there it is very chaotic. If I start and redo it again, you see that this is low level water here. Yeah, you can see that it almost touches the bottom of the channel. We can have results besides to the animation from contours using vectors or path lines to show the results. For the contours, for example, if I want to show the z velocity, it means that z along the channel. Okay, as you can see that negative sign means that negative z velocity, it is along the moving from inlet toward outlet along the channel. As you can see that here we have positive velocity, it means that it is moving backward, and here exactly what we see, recirculation, and here at these edges that these are plotted at the free surface, and also the positive velocity for z component, these are the wave traveling moving backward on the sides of the trapezoid. This is one way of the illustration, the what's going on for the velocity. For pressure, you can see that first of all at the bottom we have higher pressure, which is could be due to the hydrostatic pressure, as you can see here, and also here that we have mixing of the flow, we have higher pressure as well here. These are contours different as turbulence. We can have turbulence, for example, intensity, as you can see here. Okay, we have here larger intensities for the velocity when the flow bend and accelerate downward. Okay, you can see here higher intensity for the turbulence, and on top even for the open air, that the top surface is open to the air. Also we have even the air flow accelerated outward. These are for contours. We can have vectors, for example z component of the vectors. Okay, if we want to add the free surface, you can see again because it is z component negative value, it is in blue colors, and above there for the other colors mostly these are negative. Here you can see the direction of the flow opposite to the direction of mainstream of the flow, have the flow merging, and in this area you can see backward flow that we have. So we can see the flow pattern. Okay, this is interesting that you can see that this flow, it is like a recirculating here in this area. Here we also had higher pressures there, and at the sides these are the traveling waves moving backward against the flow mainstreams. This is for the vector using the direction of the velocity, the direction of the flow in terms of unscaled bar velocity. Also have path line in terms of the velocity magnitude. Okay, it takes a little bit time. This is the flow path line that here it display that it is for high velocity at the two channels, and here lower velocity that you can see. Okay, merging of the flow. It is a little bit slow because huge amount of the data that it shows us here. And this is the bottom view, that if we want to see higher velocity here, and you can see that have the flow here merging, and we have intensify of the flow here. So these are all different means of graphical illustration and graphical aids implemented in Fluent to see that this information about flow pattern, flow velocity, how we also see that if the waves created and propagated over the free surface, and the other things about turbulent intensity that we can have. So I hope that by this video you know that how to set up the volume of fluid method for modeling the flow analysis in open channel. Thank you very much.